And here is the lecture on electric currents, Ohm's law, and resistance. Now in this chapter we're going to talk about the flow of charges, because the flow of charges is called the electric current. Now the charges that flow could be electrons, or it could be ions, or it could be any type of charge, but electric current is the flow of electrons. So let's jump into this chapter straight away. So as shown in this diagram, we have charges that move in one direction. In real life, the charges are not all going to be moving in that orderly fashion, but there's going to be a resultant motion in that direction. And the flow of charge constitutes an electric current. But the amount of current that flows is given by the rate of flow of charge, which means how much charge flows in 1 second. So we have this formula right here, which gives I is equal to delta Q by delta T, where delta Q is the charge flowing, delta T is the time in which it flows, and I is the current. So you can see that the unit of current is ampere, because the unit of charge is coulomb and the unit of time is second. So 1 ampere is 1 coulomb per second. That means if 1 coulomb flows in 1 second, you get an electric current of 1 ampere. So here is a simple problem, just to give you the idea how much charge flows through a conductor or a calculator in this case if 0.300 milliampere flows in 1 hour. So the question is, how much charge flows through a calculator if 0.3 milliampere? So we got to change the milliampere into ampere. 1000 milliamperes make 1 ampere. So that means you got to divide 0.3 by 1000 or multiply it with 10 to the power negative 3 in order to change it into ampere, and then directly use it in the formula I is equal to delta Q by delta T. And so when you plug in the values, here I've changed the milliampere into ampere, and then you get delta Q by 3600 because 1 hour is 3600 seconds. When you rearrange and calculate, you're going to multiply it and get 1.080 coulombs. That's the charge that flows through the calculator in 1 hour. Remember, in 1 whole hour, it's only 1 coulomb, about 1 coulomb that flows through the calculator, showing already that 1 coulomb is a huge quantity of charge. So here is a circuit diagram that represents a battery connected to a headlight. So in real life you would show it as a battery connected by means of cables to a headlight, but in an electrical circuit you would represent the battery by a longer line that shows the positive and a shorter line that shows the negative. So that is the symbol for a battery or for a DC source. And then the headlight consumes power or uses the electrical current, and therefore it's called a load or a load resistance. Anything that uses electric current is called a load because it's just like carrying something. So the load consumes electricity, consumes electrical power, and so that's shown by a resistance. This will be the resistance of the headlight. That's the electrical circuit. And in this circuit, current always flows. In any circuit, current always flows from the positive to the negative of the battery. From the positive to the negative of the battery. And this is because it's assumed conventionally that the direction of current is in the flow of the direction of positive charges. So the direction of current is assumed to be in the flow direction of positive charges. So although electrons flow from negative to positive, we assume that electric current flows from positive to negative. So that's what is given here. So here are there are a couple of points here, very important points. Number one, we have to understand that in conductors, current is always by the flow of electrons. That's in conductors. But in ionic solutions or electrolytes, the flow of electricity could be either due to the flow of positive ions or negative ions. And when we come to the human body, inside the nerve cells, again, electric current is by the flow of positive and negative ions. So we could have these different types of electric currents, but always the direction of current is from positive to the negative of a see in the last chapter that there is no electric field inside a charged conductor. But in the case of a conductor, there is going to be an electric field. As you can see in this diagram, the direction of the electric field here is from left to right. That's the direction of the electric field. And we see that positive charges always move in the direction of the electric field. But if the electric current is due to the flow of negative charges, then the negative charges or electrons always flow opposite to the direction of electric field. That's another point to be noted. Positive charges flow in the direction of the electric field, while negative charges flow opposite to the direction of the electric field. And that's what I've written here. An electric field exists inside a conductor, and positive charges again flow from left to right or in the direction of the field. So positive charges move in the direction of the field, negative charges move opposite to the direction of the electric field. And here is a simple question that we're going to work out. We got to calculate the number of electrons that flow. Okay, the number of electrons that will flow in order to constitute a current of, let's say, 1 ampere. So how many electrons would have to flow every second? I forgot to mention that. How many electrons would have to flow in 1 second to constitute a current of 1 ampere? Now, in order to do that, we start with the basic formula of current, which is current is charge divided by time. And so because we're looking at 1 ampere, it's 1 coulomb per second, and 1 coulomb is a certain number of electrons multiplied by the charge of the electron. And so we can find the number of electrons necessary by dividing the charge, which is 1 coulomb, by the charge of an electron. So whatever charge needs to flow divided by the charge of the electron, and we will get the number of electrons, which in this case is a huge number. We get 6.25 times 10 to the power 18 electrons have to flow in order to constitute just a current of 1 ampere. Next up is the idea of drift velocity. So when charges move through a conductor, for example, when electrons move through a conductor, these electrons are continuously colliding with the atoms in that conductor. So the flow of electrons is not smooth. They are continuously colliding and then picking up speed again. Again they collide. So that means the electrons are just moving really slowly. So here's a question now. As soon as you flip a switch, the lights come on. which makes us think that the electrons are flowing that fast. No, it's not the electrons that flow that fast. It's the electric field that goes from the switch to the light bulb at the speed of light. So what am I saying? I'm saying that although electrons flow really slowly, the electric field in the conductor moves very fast. So let's look at the speed of flow of electrons. It's called the drift velocity because it's simply drifting. Now, usually the drift velocity is about 10 to the negative 4 meter per second. That's so slow. 10 to the negative 4 meters in a second. And we will just work out one problem to look at the real drift velocity in a copper conductor. All right. So the electric field, remember the electric field is the one that changes at nearly the speed of light, although the electrons are moving slowly. So here you can see the multiple collisions made by the electrons as they try to move through the conductor. Drift velocity is represented by V sub d, and it is defined as the average velocity of the electrons or the free charges in a conductor, because not all of the electrons will have the same velocity. So we got to take the average velocity of the free charges, right? And here we're going to get an idea, a formula for drift velocity. So we have a conductor, a part of a conductor, which has an area of cross-section A. It has a length. We're looking at a section which is of length x. Assuming that the drift velocity is v sub d, displacement is given by velocity multiplied by time. So an electron at this point would move to this point over a displacement x, which is given by its drift velocity multiplied by time. I think you got that. So drift velocity multiplied by time gives you how much the electron moves. And also let's assume that in this material there are n free electrons in 1 meter cube. Now remember that electricity is due to the flow of free electrons. And if you take a conductor, a metal, there are a huge number of free electrons in every meter cube. So if there are n free electrons in every meter cube, we have to first find the total charge in that section. And the total charge in the section is given by Q, which is the charge of one electron, multiplied by N, which is the number of free electrons in 1 meter cube, and then A times X. What does that give you for a cylinder? A multiplied by X. Area times length gives you the volume. So when you multiply N with AX, you're going to get the total number of free electrons in that entire volume. And so the total number multiplied by the charge of an electron gives you the total movable charge. You get the total movable charge, and that when you divide by time, you get the current. But what's interesting is in this formula, x divided by delta t. Now what is that? X is the displacement, delta t is the time, and when you divide displacement by time, you get velocity. So that is the drift velocity. So in the next step, I am going to replace x by delta t by drift velocity, as I've done here. And remember, n is the number of free electrons in 1 meter cube, not in the whole conductor. A, again, is the area of cross-section. And usually it will be circular in shape, which means the area would be pi r squared. Q is the charge of each charge carrier. Q is the charge of each carrier. So now let us calculate the number of free electrons in 1 meter cube of copper. So the material copper has been specified and you will be given its atomic weight. And we also know that in copper there is one free electron per atom, and now that will also be given. In copper there is one free electron per atom. So we would have to first find out the number of atoms in 1 meter cube, and then that will give us the number of free electrons in 1 meter cube, because there's one free electron for every atom. And then we'll have to multiply that with the charge of an electron to give the to get the total charge. Okay, so let's do that. So n, to calculate n, which is the number of electrons in 1 meter cube, you'll have to go, there's one electron per atom, and the Avogadro number gives you the number of atoms per mole. Okay, the number of atoms per mole is 6.02 times 10 to the 23, and then because the atomic weight of copper is 63.54, that many grams will make 1 mole. So here 1 mole per 63.54 grams, and then 1,000 grams make a kilogram. And then the density of copper is given, because density shows you how much mass exists in 1 meter cube. So you have the density of copper in kilograms divided by 1 meter cube. So if you look at those units, you see that the atoms and the atoms get cancelled here, and you have the mole and the mole cancelling off. You have the kilogram and the kilogram again cancelling off, and finally you're left with the number of electrons in 1 meter cube. Okay, so you got to look at this and carefully think about it. There's 1 electron per atom. There are Avogadro number of atoms in 1 mole, and 1 mole of copper is 63.54 grams, but we got to change it into kilograms, which is 1,000 grams, and then we got to know how much kilograms or how many kilograms there is in 1 meter cube, which is actually the density. So when you do all that, you get this large number. You get 8.342 times 10 to the power 28 electrons in 1 meter cube. Now you know why copper is a good conductor, because there are that many free electrons in every meter cube of copper. So here let's do another question. Let's continue with this and try to calculate the drift velocity of the electrons in the copper. All right, and I assume that it's a current of 1 ampere that's flowing, and the radius of the conductor is 2 millimeters. So now we got to find the drift velocity, and in order to get the drift velocity, we have that formula that connects the electric current with the drift velocity. But before that, let's find the area of cross section. The area of cross section is pi r squared, where r is the radius, but the radius got to be in meters, so it's 2 times 10 to the negative 3, and so you get the area of cross section. And then I is equal to NA V sub dE, and make velocity the subject, rearranging it, and then substitute the value of current as 1 ampere, and we just got the number of free electrons, 8.342 times 10 to the 28 in every meter cube, so we know that. And then the area we just calculated, and then you also have the charge of an electron. So when you plug in all those numbers and calculate, we get this as the drift velocity, 5.965 times 10 to the negative 2 meter per second. So you can see that the drift velocity is really a small number. Law in electricity is called Ohm's law. And if you look at this circuit, you see it represents a battery connected with a resistance. And according to Ohm's law, the current flowing through a conductor is directly proportional to the voltage across the ends of the conductor. Again, the current flowing through the conductor is proportional to the voltage maintained across the ends of the conductor. Now, how do you maintain a voltage across the ends of a conductor? By using a battery. So, which means if you use a more powerful battery, you're going to get a bigger current. If you double the voltage of the battery, you're going to get double the current flowing through that resistance. So, resistance of a conductor is a constant, but there is a condition. The temperature must be maintained constant because the resistance changes with temperature. So when we state Ohm's law, we have to remember to state that condition. So let me state Ohm's law one more time. The current flowing through a conductor is directly proportional to the voltage across the ends of the conductor, provided the temperature is constant. So mathematically, now you get this formula that current is voltage by resistance, or it's a better way when you put it this way because it's easy to remember. I say, hey, it's a very important rule. It's a very important rule. Voltage is equal to current multiplied by resistance. This is the most basic law in electricity. And which means that to get 1 ampere of current with 1 volt, the resistance must be 1 ohm. Oh, there I'm introducing the unit of resistance. The unit of resistance is called ohm, but it's represented by this Greek symbol called omega. So omega represents an ohm, and 1 ohm is always 1 volt divided by 1 ampere. What does that mean? That means if you have 1 volt across a conductor and you get a current of 1 ampere, for sure the resistance of that conductor is 1 ohm. So let's work out a simple problem so that will give you a better idea. So let's say that the voltage is 12 volt and the current is 2 ampere. What's the resistance? Simple. Resistance is voltage by current. It gives you 12 volt by 2 ampere, which is of course 6 ohms. So 6 ohms is the resistance of the conductor. Circuit, actually the same circuit that we've been looking at. And in this case, we have a voltmeter connected across the resistance. A voltmeter, of course, measures voltage, and whenever a voltmeter is used, it's always connected in parallel to the resistor. A voltmeter is always connected in parallel because you want the same voltage across the resistance to appear across the voltmeter. So here is the circuit diagram. So let's assume that the voltage of the battery is 9 volt and that it sends a current of 2 ampere through this resistance. Now, what does the voltmeter read is the question. What does the voltmeter read? The voltmeter will surely read 9 volts. So in this case, the voltmeter reads 9 volts because the voltage across the resistance is going to be 9 volt. And the current through the resistance is 2 ampere. If that's the case, the resistance is 9 divided by 2, 4.5 ohms. So that's the resistance of this resistor. Actually depends on 4 factors. The resistance depends on the material, whether it's copper or aluminum or any other material. That's number 1. Resistance depends on the material. Number 2, the resistance depends on the length of the conductor. If the length of a conductor is bigger, then its resistance is going to be bigger. Number 3, the resistance depends on the area of cross section, but it's an inverse dependence, which means if it's a bigger area of cross section, like a thicker cable, like a thicker wire, then its resistance is going to be small. So So remember, thick conductors have a smaller resistance. Thin conductors have a bigger resistance. And the fourth factor that we will not look at now, on which resistance depends, is the temperature. So we will look at that separately. For now, let's assume that the temperatures are constant. If that's the case, resistance depends on these three factors: the material, the length, and the area. And as you can see here, this symbol, which represents resistivity, it's rho in Greek, it represents resistivity. That's the material, that depends on the material. And you see that the length is in the numerator and the area of cross section is in the denominator. So that's the formula for resistance in terms of length and area of cross section. Now, what do you mean by resistivity? Resistivity is actually the resistance of a conductor of length 1 meter and area of cross section 1 meter square. So if you take a big enough conductor that has an area of 1 meter squared, that's going to be a large one, and a length of 1 meter. And if you find its resistance, you will get the resistivity of that material. So that formula is important. And here I'm again explaining that L is the length. It should be in meters. A is the area of cross section, which most of the time will be pi r squared because the cross section would be circular. And rho is called the resistivity, which depends on the material. And the unit of resistivity is ohm multiplied by meter. Ohm meter, okay? And like I told you, it's the resistance. So let's calculate this. A resistance of 1 meter copper wire of radius 1 millimeter. What is the resistance of 1 meter of copper wire of radius 1 millimeter? And its resistivity is given here. So we just got to use this formula. First we got to find the area of cross section, but area of cross section is pi r squared, so I'm going to put it that way. Pi times radius is the value of the resistance is 0.0054 ohms. Now we will look at the fourth factor, namely the temperature. I've been mentioning that the resistance depends on temperature. So if you look at this graph, you can see that the temperature is in Kelvin on the x-axis and the resistance is in ohms on the y-axis. And at this part of the graph shows you that as the temperature increases, the resistance also increases. That's for conductors. So for all conductors, as the temperature increases, the resistance also increases. And that means as you cool a conductor, you're going to have a decrease in resistance, and there's going to be a particular temperature at which the resistance becomes zero. Now that is called superconductivity. So superconductivity is when the resistance of a conductor becomes zero. All right, so that's what the graph shows here. And the formula for change in resistivity with temperature is similar to the formula for change in resistance with temperature. We'll take one at a time. So the formula for change in resistivity with temperature involves the resistance at room temperature, which I'm going to show in the formula in a second. So here is the formula, and in this formula, rho is the resistivity at any temperature. So maybe at a high temperature. Rho naught is the resistivity at room temperature. And in physics, the room temperature is taken as 20 degrees Celsius. So rho naught is the resistance at 20 degrees Celsius. Rho is the resistivity at any other temperature. Alpha is a constant for each material. and it's called the temperature coefficient of resistance. The temperature coefficient of resistance. And delta T is the change in temperature, which means if you're looking for resistivity at 60 degrees Celsius, 60 minus 20 is 40. So delta T would be 40. Okay, so remember, alpha is a constant, another constant. It's called the temperature coefficient of resistance, and its unit is per degree Celsius. It just shows how much it changes for 1 degree Celsius change in temperature. So here is a question. The alpha of aluminum is given 3.9 times 10 to the negative 3 per degree Celsius. That's the temperature coefficient of resistance of aluminum. And the change in temperature is 2500 degrees Celsius minus 20 degrees Celsius. So that means we are trying to find the resistivity at 2500 degrees Celsius. And we're given the resistivity at 20. So the difference in temperatures is 2480 Celsius. And then the formula for resistance, the change in resistance is just similar to the formula for change in resistivity. So a similar formula, plug in the numbers. Resistance at 20 is given as 0.5, and then you have 1 plus alpha multiplied by the change in temperature. And when you do the math, you get 5.336 ohms. Now looking at this problem, you might think, oh, that the change in temperature causes a big change in resistance. That's not true. Remember that here the change in temperature is really big. It's 2480 Celsius. That's why the resistance increased from 0.5 to 5.336 ohms. All right, so also remember, for semiconductors like silicon, germanium, carbon, etc., alpha is negative. That means when the temperature increases, the resistance decreases. Now, let me not confuse you. For all conductors, when the temperature increases, the resistance increases. But for semiconductors, when the temperature increases, the resistance now decreases instead of increasing. That's the difference. Real life application of change in resistance with temperature, which is in a digital thermometer, you would see that, because in this thermometer you use a material called a thermistor that really has a big change in resistance with temperature. So even a small change in temperature causes a big change in resistance, and that's a thermistor. So we use a really small quantity of that thermistor in a digital thermometer to get the accurate temperature of a patient. So that's a real life application. And next we have to talk about electrical power. For example, we know that different equipment used at home consume different power. Like the air conditioner consumes a lot of power. A refrigerator consumes much less than that. And an electric light bulb consumes really small power. If it's an LED bulb, then it consumes really small amount of power. So what is electric power? That's what we're going to look at here. Let's talk about electrical power. And the formula for power is work over time. And work is measured in joules, time in seconds, and so the unit of power is watt. Okay? And work in electricity is the product of charge and voltage. So that's why we get Q times V, and then Q by T. What is Q by T? Charge by time. Yes, charge by time is electrical current. So we get the formula for power as the product of current and voltage. But we can have two other formulas, because we can substitute for current as V divided by R here, and when you substitute that, you're going to get V squared divided by the resistance, or if we substitute for voltage as I times R here, then you're going to get I squared times R. So you can have three formulas, but there's one important thing. The formula that I've put in a circle works all the time. That means it works for any type of material. That's what I mean, for any type of material. But the other two formulas only work for conductors. It will not work for other types of materials like semiconductors. So here is that circuit that we had used before, exactly the same circuit where you have a 9-volt battery supplying a current of 2 ampere through a resistance. Let's calculate the power consumed by the resistance. All right, calculate the power. In this case, we have the current and we have the voltage. So naturally, the formula for power that we'll be using is I times voltage, which is 2 ampere multiplied by 9, which gives 18. Well, that's not 18 joules. It's supposed to be 18 joules per second. Let me write that now. 18 joules per second, or 18 watts. As you can see, you could have expressed it as ampere times volt. So ampere times volt is the same as joule per second, or one is called an alternating current, and that's the type of current that we get at home. But the second type of current that we've been looking at so far, supplied by batteries, is called a direct current or a direct current. So you have alternating currents and direct currents. And the graph here really shows you the difference between the two. Now, a direct current, the current and voltage remain constant. It does not fluctuate. It does not change. So when a battery supplies current, it stays at a constant rate. Well, of course, until the battery is about to die, right? So most of the time, 95% of the time and 98% of the time, a battery supplies a constant current. So that's called direct current. It's not only that the current is constant, it's only flowing in one direction. Do you remember the direction? I hope you do. It flows from the positive of the battery to the negative, always. So the value of the current and its direction both remain the same in direct currents. But in alternating currents, just by the word you know, it alternates between positive and negative. That means one half it's flowing in one direction, in the next half it's flowing in the opposite direction. So the direction alternates. And that's why an alternating current or voltage is represented by a sine wave. This is a sine wave. It has a positive part, it has a negative part. See that? So you have the green one showing the voltage and the red one showing the current, and both fluctuate, both alternate. So when you try to study alternating currents, you see that there is a maximum value for the voltage, which is called the peak value. It's V0. Similarly, there's a maximum value for the current, which is called the peak value of current, which is I0. And once we try to take the average, we take it in a particular way, because if you simply take the average of this, you're going to get 0, because there's equal positive and negative. So you take it in a particular way, and then you get the what's called the RMS value, the root mean square value. So it's the RMS value, and the RMS value is related to the peak value. So you got to know that relation. But before that, this is how an alternating voltage is represented. Let's look at those terms. V is the voltage at any instant. Remember, the voltage keeps changing, right? So at any time t seconds, you could find the voltage using this formula. And V0 is the peak value. F is the frequency. It's how many cycles are produced in a second. At home, we have AC, which is distributed at 60 cycles per second, 60. So the frequency could be anything, and when you know the frequency, you can calculate the voltage at any instant by knowing the peak value of the voltage. Similarly, there is an expression for current, which is once again I is equal to I naught sine 2 pi ft. Exactly the same. And remember, by Ohm's law, I naught would be V naught by R, right? The peak value of current is the peak value of voltage divided by resistance. And power, we've talked about electrical power. Power is given by this formula. It's I squared of the RMS value multiplied by the resistance. And I RMS is I naught by root 2. Similarly, V RMS is V naught by root 2. When we work out problems, this will become even more clear. Let me just give you an example right away. At home, we get AC at 120 volt. Most of you know that. Now, when we say 120 volt, that's actually the RMS value. So the peak value is going to be much higher. The peak value is going to be 120 multiplied by root 2. Okay, just remember that. So whenever we talk, by default, when we talk about voltages, we talk about the RMS value of voltage. At the end of this chapter, let's talk about electrical hazards. You got to be really careful. What you have here is what's called a short circuit. So what it is this is an appliance that you are using, and the current is supposed to flow through the cable into the appliance, complete the circuit and back again. But due to some fault or some defect, there is a short circuit here. Now, a short circuit, the name itself shows it's a shorter path. So now the current will reach the short circuit and actually will complete the circuit without going through the equipment. So it may be that one part of the conductor is touching the body of the equipment. So current always chooses the lowest resistance path. So instead of going through the whole equipment, it will take the shorter path now. Now the shorter path has a much smaller resistance. And when the resistance is small, the current is going to be really big. And when the current is big, there's going to be a lot of power or a lot of heat produced, which can actually produce a fire, or something is going to melt. In order to avoid this from happening, we have protective devices, which may be an electrical fuse, or it could be a circuit breaker. A circuit breaker is many times advantageous compared to an electrical fuse, but we use both. So let's make some calculations. Here is the electrical circuit to show you the actual path should have been this, but now the short path is this one. And the short circuit resistance is assumed to be 0.1 ohm. And if it's a 120 volt generator, we're going to get a huge current. The current is 120 divided by 0.1, which is going to be 1200 ampere. And therefore the power, which is I squared times R, is going to be very large. It's 144,000 watts. That's high. That's 144 kilowatts. That's really high. That's why we need to have protective devices like I mentioned. Here you have two. On the left side you have the fuse. That's a cartridge type fuse there. And then on the right side you have a circuit breaker. The fuse actually is made of an alloy of tin and lead, which has a low melting point. So in case there is, overheating in any part, this is the part that's going to melt because it has a low melting point. It's going to melt, which will break the circuit. So it really acts like a switch which opens the circuit and protects from a fire happening. But now on the right side, what you have as a circuit breaker could be magnetic, but in this case it's a thermocouple. Now a thermocouple, or I should say, it's a bimetallic strip. So you have two different metals connected together, and when they get heated, it's going to bend because one metal expands more than the other, and when it bends away from the electrical contact. So it's like that. If this is the contact, it bends away and opens the circuit. So that's one type of event of an electrical shock. Two things can happen. Number one, because of the involuntary muscle contractions, the victim can be just thrown off from the electrical cable or from wherever he's touching the live wire. He can be thrown off, which in one way is better, as compared to the second case where the muscles that actually close the fingers become stronger than the muscles that let them open it. So when you touch that live wire, your muscles that close it are stronger, and so the victim just holds on to it, which means that the current continues to pass through the victim, which could lead to a very dangerous situation. So what's important is to make sure that the fuses are working and that the circuit breakers are tested every now and then to make sure that this kind of a thing does not happen. All right, so hopefully you've understood electric currents, Ohm's law, resistance, power in electrical circuits, and finally I hope you understood that electricity is very useful but could be dangerous. And now if you understand all this, don't you want the others to hear about it? So please like the video, subscribe so you get the new ones, and let me see a comment there which would help me to make the videos even better. Thank you. You have a good one.